Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore how large language models learn to follow instructions through instruction tuning, human feedback, and the training methods that reshaped modern AI alignment.
It's really hard to overstate what a massive turning point this was. I mean, for you listening at home, when you use modern chat models, this whole alignment process is the reason they feel helpful and reliable.
Instead of just frustrating and, well, kind of verbose.
Exactly. Because if we rewind just a few years, the first generation of large language models, the early versions of GPT-3, they were just these incredible demonstrations of raw knowledge.
Right.
They'd read colossal data sets. They were brilliant, but often completely useless for a specific task.
That's really the core of it, isn't it? That whole unruly genius idea. You had this system that knew so much, it could generate perfect complex text on almost any topic.
Anything.
But then you'd ask it to do something specific, something constrained, like write a haiku about the Roman Empire, and what would you get?
You might get a 3-paragraph essay or, a poem with 7 lines. The knowledge was all there, but that ability to just take direction, to actually follow the instructions, was just profoundly missing.
So it wasn't that the model was being difficult. It was just a fundamental mismatch in its objective.
Precisely. It was optimized for one thing and one thing only: statistical likelihood. Its entire mission during that pre-training phase was to be the world's best predictive text engine.
Just predict the next word.
Just predict the next token that makes the most sense. So it was fantastic at continuing a thought, but it just didn't have the architecture to be, goal-driven.
Yeah.
If you gave it subtle constraints like a word count or a specific format, it just saw those as more text to predict from.
Not as rules to obey.
Not at all. It was a mismatch between the model's goal prediction and the user's goal, which was assistance.
And this wasn't just a feeling people had. Researchers had to put some hard numbers on this failure, right?
Absolutely. The first attempts to fix this gap, they tried using existing NLP datasets. The thinking was, okay, if we just show the model enough structured tasks like translation or question answering, it'll generalize.
So they looked at big datasets that were used to build models like T0 and FLN.
They did, and the goal was to teach it by showing it a huge breadth of academic tasks. But it failed pretty dramatically when they tested it against how real people use these things.
Because academic tasks aren't the same as just a person typing a random question into a box.
Not even close. The crucial finding, really the insight that led to all of this, was that public NLP datasets just do not reflect the messy, spontaneous prompts that real people write.
So what did the numbers actually show? The evidence must have been pretty stark.
Oh, it was staggering. When they tested those T0 and FLN models against a really simple baseline, just a basic supervised fine-tuning or SFT, they actually performed a little bit worse. Slightly worse. But the real metric was human preference. When you put the outputs side by side, humans preferred the later aligned model, something like InstructGPT, with a massive win rate of 73.4% against that simple SFT baseline.
Okay, wow. And the T0 and FLN models?
They only got a human preference rating of around 27% to 30%. It was dismal.
So almost 3/4 of the time, people just knew the other output was better. That's a huge signal.
It's an undeniable signal. It proved that to make a helpful assistant, you have to train it on what helpful assistance actually looks like, not on academic benchmarks.
So the gap proved that this instruction-following data was the key. Which brings us to that first logical step you mentioned, supervised instruction tuning, SFT.
SFT is really the foundation. It's the step that teaches the model the basic grammar and pattern of an interaction. It's like teaching it, okay, when a human gives you instruction, this is what a good response should look like.
So it's not unstructured reading anymore. It's almost like focused flashcards.
That's a perfect way to put it. It's about showing the model thousands of curated examples. Here's the instruction, here's the input, and here is the ideal output.
So an example would be instruction. List 5 takeaways from this text. Input, a block of text, and then the output would be a perfectly formatted list.
Exactly. And in the early days, that SFT data set was actually pretty small, maybe around 13,000 training prompts. But what was really important was that they mixed in prompts written by human labelers with actual customer API prompts.
So they injected that real-world messiness right from the beginning.
Right from the start.
But 13,000 examples, that still feels tiny compared to the trillions of words in the pre-training data. Why was that so effective?
Because it was incredibly targeted. The model, remember, already has all the knowledge. SFT isn't about teaching it new facts. It's about teaching it how to control the facts it already knows.
It's giving it the switch to go from being a predictor to being an actor.
A constrained actor. But for that to work, the dataset had to be exceptionally diverse. It needed to cover the whole range of things people might ask.
And what does that diversity look like? I mean, we're not just talking about summarizing articles.
No, not at all. You need everything. Brainstorming, like, give me 5 ideas for zero waste packaging. Classification, like, rate the toxicity of this comment from 1 to 10.
Complex stuff, too, I imagine.
Oh, yeah, really complex extraction. Things like pull all the financial data from this earnings report and structure it as a JSON object. Or open-ended questions like explaining the cultural significance of the Silk Road.
I remember seeing examples like asking it to write rap lyrics based on an article, or explaining a complex topic to a second grader.
Exactly. And those are so important because they force the model to interpret subtle, non-literal intent. It has to be accurate, concise, and use the vocabulary of a second grader all at once. Training on that wide range is what gave it the ability to handle brand new tasks it had never seen before.
But that sounds incredibly labor-intensive to create. I mean, 13,000 high-quality, diverse examples. That's got to be expensive.
It is, and that's where the next big innovation in SFT came in. It's a technique called self-instruct. This was the moment researchers realized they could use the powerful model they already had to help generate its own training data.
The model teaching itself. Now, hold on. I'm a bit skeptical here. Doesn't that risk the model just reinforcing its own biases?
Yeah.
Couldn't it just generate 50,000 versions of the same 3 tasks it's already good at?
That's an excellent follow-on, and it's something the researchers were very aware of. The key to avoiding that trap is in the initial seed tasks and the filtering process.
How does it work?
They start with a very small, very carefully curated seed pool. In one case, it was only 175 human-written tasks. But these were examples of really diverse, well-posed problems.
So really high-quality example.
The best they could make.
Yeah.
Then they prompted the model with these examples and basically instructed it to start generating new instructions, new inputs, and new outputs, but in the same style of novelty.
It's like showing an apprentice 175 perfect examples and then saying, okay, now make 50,000 more, but keep the quality just as high.
That's a great analogy. And they used clever filtering, things like clustering algorithms, to make sure the new prompts weren't just rehashes of the old ones. They were actively trying to maximize the variety.
And this bootstrapping method, it actually worked.
It worked incredibly well. They generated huge data sets, over 52,000 instructions in one case. And because the model wasn't limited to academic tasks, the data it created felt much more like real-world, general-purpose problems.
So what was the performance like? Did it really compare to data labeled by humans?
It got remarkably close. When they fine-tuned a model just on this self-generated data, its performance was nearly on par with an early Instruct GPT model. It closed all but about 5% of the performance gap.
Wow. So that proved that self-instruct was a really scalable, cost-effective way to build that foundation. But you said it couldn't close the final gap.
Right. SFT gives you the structure, but it doesn't solve that deeper philosophical conflict between prediction and preference.
The model is still, at its core, designed to predict the next token. It's not trying to be helpful in a focused way. It's just trying to be statistically likely.
And that's the goal that had to shift. It had to move from optimizing for prediction to optimizing for human alignment, following user intent, even when that intent is ambiguous or complicated.
This is where that idea of alignment really started to become concrete in AI research.
It is.
So you can't use a simple metric like accuracy. How do you even define if an AI is good in a way that goes beyond just following the rules?
Well, researchers settled on 3 main pillars to define alignment: helpfulness, harmlessness, and truthfulness. These became the sort of non-negotiable criteria for a useful assistant.
And helpfulness is more than just doing what you're told. Yeah.
Oh, absolutely. It's 2 things: adherence, which is following the explicit rules, like formatting, and inference, which is about interpreting the user's underlying intention.
So if a user asks about football, a truly helpful model has to infer the context. You shouldn't just assume American football.
Exactly. It needs that conversational intelligence. It might need to ask for clarification or provide a balanced answer that acknowledges the ambiguity.
That makes sense.
Yeah.
What about truthfulness? I mean, how do you measure honesty in a machine that doesn't really believe anything?
You can't check its internal beliefs, so you have to measure observable truthfulness. You focus on verifiable claims about the world.
And you do that by testing for hallucinations.
Right. You measure its tendency to just make things up in closed domain tasks where you know the right answer. And you can also use specialized data sets like Truthful QA that are designed to trick models with plausible sounding but factually incorrect statements.
And then there's harmlessness, which feels like the most subjective and culturally dependent one.
It's by far the most challenging. Early on, defining harmful was tough because it's so context-dependent. So to make it operational, they relied on proxy criteria.
What kind of criteria?
Labelers would assess outputs based on whether they were inappropriate for a customer assistant, whether they denigrated a protected class, race, religion, sexual orientation, or if they contained explicit sexual or violent content.
So you have these three criteria, all of which are pretty nuanced and can sometimes conflict with each other. It sounds like no simple algorithm could capture all of that.
And that is the absolute key insight of this entire phase of research. You cannot automatically quantify the trade-offs between helpfulness, truthfulness, and harmlessness. The only metric that worked was human judgment.
So human preference ratings became the gold standard.
They did, whether it was a Likert scale or just a simple which one is better. Comparison, that subjective human taste, became the signal. And that necessity is what gave rise to RLHF.
So if SFT taught the model the grammar of instruction, then reinforcement learning from human feedback, RLHF, is what taught it etiquette, the taste and manners to actually satisfy a user.
That is the perfect analogy. RLHF is this three-step process that finally closes that alignment gap. And it all starts, as we said, with that SFT-tuned model. That's your baseline.
That's step A. And step B is where you train the reward model. This is where the human contractors come in to define the AI's taste.
This is the most critical data generation phase. A team of human contractors, it was about 40 people in the early days, mostly English speaking, were hired and screened for their sensitivity and consistency in evaluating outputs based on those three criteria.
And what were they actually doing? They weren't just saying good or bad, were they?
No, their task was ranking. For any given prompt, the SFT model would generate a whole range of outputs, usually between 4 and 9 different responses. The labeler's job was to rank all of them, from best to worst.
So they're explicitly collecting comparison data. It's not just about an absolute score. It's about relative preference.
Exactly. And this massive data set of comparisons, I think one of the early reward model data sets used around 33,000 prompts, is then used to train a totally separate AI.
Which is the reward model, or RM.
The RM. And its only job is to mimic human preferences. It learns to take a prompt and a response and output a single number, a reward, that predicts how highly a human would have ranked that output. It becomes your automated, synthetic human critic.
That makes a lot of sense. But training a model on that kind of comparative data, where all the examples for one prompt are so similar, sounds like it would be really prone to overfitting.
That's a great technical point, and it was crucial to making RLHF stable. If you just shuffled all the comparison pairs from the whole data set, the model would quickly overfit.
So what did they do?
Instead of shuffling them, they treated all the comparison pairs from a single prompt as a single training batch. So the model learns to make one cohesive ranking decision for that whole group of responses, which prevents it from learning weird shortcuts based on that one prompt.
That's a very clever solution. So now you have the RM, your automated critic. And this brings us to the final step, using reinforcement learning to actually optimize the model.
This is the final stage, and it uses an algorithm called proximal policy optimization, or PPO. We take our SFT model, which we now call our policy, and we basically put it in a training loop where the reward model provides all the feedback.
And the model's goal is just to maximize that reward signal from the RM.
That's its only goal.
So PPO is one of those terms we hear all the time. Can you break down what it's actually doing here?
PPO is essentially a very stable, conservative way to adjust the language model. The key thing it does is it penalizes large updates to the policy. It makes sure that as the model learns to get a higher score, it doesn't suddenly forget all the knowledge and fluency it learned during pre-training.
So it's making small, controlled adjustments. It's gently steering the model toward what humans prefer without letting it go completely off the rails.
Precisely. The LLM generates a response, the RM scores it, and PPO uses that score to adjust the LLM's parameters to maximize the reward. And the best part is this whole RL loop is done on a big data set of prompts that don't need any new human labels.
Because the reward model is providing that signal synthetically.
Exactly, and that's the decoupling that makes the whole thing scalable.
And the payoff for all this complexity was just massive. The shift from interacting with a raw GPT-3 to an RLHF-tuned model was a complete behavioral transformation.
It was a foundational leap. I mean, human labelers preferred the outputs from the RLHF-tuned Instruct GPT over the original GPT-3 an astonishing 85% of the time.
85%.
And even if you tried to help the original GPT-3 by giving it examples in the prompt, a technique called few-shot prompting, the RLHF model still won 71% of the time. It just proved that training directly on preference is fundamentally more effective.
And it's that consistency that really matters. It means you can actually build these models into applications and trust that they'll follow the rules you set.
That reliability unlocks everything. The alignment process gave them specific, measurable improvements across the board, in control, in truthfulness, and in appropriateness.
Can you walk us through some of those concrete examples, the ones that really show the difference in control?
A great one is coding tasks. If you gave the old GPT-3 a snippet of code and asked a specific question about it, it might just guess the answer, maybe give you multiple choice options, like it was a quiz.
But the Instruct GPT model would infer the user's intent.
Exactly. It understood the user wanted a full descriptive explanation of the function, and it provided that. It shifted from being a quiz taker to being a collaborative explainer.
What about those really annoying specific formatting requirements that are so important for data pipelines?
That formatting example is maybe the best illustration of RLHF's power. There is a prompt that asks the model to extract positive and negative trends from a passage and list them as bullet points.
But with really specific rules.
Incredibly specific. Use a hyphen as a bullet point, capitalize the first word, and put a period at the end of each one.
And if you've ever tried to get an older model to stick to rules like that, you know it's a coin flip.
The original GPT-3 just failed. It would usually output a rambling, unformatted paragraph, but the RLHF-tuned model delivered it perfectly. It followed every single constraint to the letter.
So the reward model successfully penalized any deviation, and that taught the policy to be strictly compliant.
Exactly. And that's not just cosmetic. That's how developers can ensure that data extracted by an LLM is actually usable in the next step of a program. It makes the models into reliable tools.
So the strength of RLHF is pretty undeniable. It created this scalable feedback loop that really changed the game. But as with anything involving human judgment, it's not perfect.
Not at all. When you put humans in the loop, you inherit all their limitations and biases. And RLHF, especially in its first form, raised some really serious challenges.
Let's start with the labelers themselves, the source of all that preference data.
The main limitation is just labeler representation. The model is being aligned to the preferences of a pretty small, specific group of people. We're talking about maybe 40 contractors, mostly English-speaking, from a few specific regions.
So the AI's idea of what's helpful or appropriate is inherently filtered through a very narrow cultural lens.
It is, and that's a huge challenge. And even within that small group, they didn't always agree. The interlabeler agreement rate was only around 73%.
So they disagreed with each other over a quarter of the time.
They did, which just shows you that alignment isn't about finding one objective truth. It's about aligning to the subjective consensus of a small committee.
And that subjectivity, that leads right into the core dilemma.
Yeah.
The conflict between being helpful and being harmless.
Right, because the initial RLHF training, it generally prioritized being helpful to the user who wrote the prompt.
Which sounds like a good thing, but if I ask the model to do something harmful in its effort to be helpful, it might just do it.
And that's exactly what happened. It created this really counterintuitive result. When researchers explicitly told the PPO models to be biased, a prompt like, complete the sentence using maximally offensive language, they generated more toxic outputs than the raw, unaligned GPT-3 model.
That's shocking. The aligned model, which was supposed to be safer, actually became more dangerous when the user wanted it to be.
Because it was so well aligned to following the instruction, even a malicious one, it was being helpful to a harmful user. This really exposed that tension. Who's the model aligned to? The user or some broader safety standard.
And later methods had to be developed to address that specific loophole.
Yes, things like safety overrides or constitutional AI, which basically make the harmlessness rules non-negotiable. But the initial version of RLHF showed that just prioritizing helpfulness was a double-edged sword.
And on top of all that, there's just the massive cost of it all. Hiring dozens of expert labelers is expensive and slow.
That financial constraint is a huge driver of all the research that came next, which is all about shifting from just using more human labor to making the feedback loop more efficient and automated.
But before we get to the automation, it's important to stress that SFT and RLHF, they really work together.
They're a perfect pair. They're sequential and complementary. SFT teaches the model the basic structure. If you ask for a summary, this is what a summary looks like.
And that RLHF comes in and applies that qualitative polish.
It teaches the model the style and the quality. This summary is better than that one because it's more concise and it focuses on the points the user actually cares about. Together, they create that refined, goal-driven behavior.
So given all the costs and biases of doing this with human labelers, the next logical step was to figure out how to do it more efficiently.
This led to a rapid acceleration in alignment automation. One of the first big ideas was something called RLTHF, or targeted human feedback. The goal is just to maximize the return on investment for every single human annotation.
So it's about being smart with where you apply that expensive human expertise.
Yeah.
How does it figure that out?
It uses a really clever feedback loop. It starts by using a very capable foundation model, like a super expert, to provide the first round of preference labels. That's cheap. Then you train a reward model on that AI-labeled data.
And the key is using that reward model to find its own blind spots.
Exactly. The RM can identify the hard-to-annotate samples, the places where the AI labeler and the RM disagreed, or where the RM's own confidence was really low. These are the inputs the AI found confusing.
So instead of a human ranking 100 random responses, the AI filters 10,000 down to the 600 most ambiguous ones and only asks the human to look at those.
Precisely. And by focusing human expertise on just the most challenging 6% or 7% of the data, researchers showed they could achieve the same gold standard quality as full human annotation, but with a tiny fraction of the labor.
That's a huge efficiency gain.
Yeah.
But are there methods that try to get rid of human preference ranking entirely?
Yes, and that's where you get into explorations of adversarial training, often called RLGAF, or reinforcement learning from generative adversarial feedback. It basically borrows the structure of GANs.
So if the LLM is the generator, what's playing the part of the reward model?
The reward model is replaced by a discriminator. The discriminator's only job is to tell the difference between real examples from the domain you want, say high-quality examples, and the fake examples generated by the LLM.
And the LLM's goal is to fool the discriminator.
Exactly. The discriminator's failure to tell them apart becomes the reward signal for the LLM. So the model learns to align itself to the style of the high-quality examples.
What's the main advantage of that approach?
The big one is sample efficiency. You can align a model to a very specific style, say, technical documents from NASA, just by showing the discriminator a bunch of NASA documents as the real data without needing humans to rank anything.
But GAN training is notoriously unstable.
Very unstable. You run into major risks like mode collapse, where the model just finds one good answer and repeats it over and over. Or vanishing gradients, where the discriminator gets too good too fast and the LLM just stops learning. It's high risk, high reward.
So all of these methods, SFT, RLHF, even RLGAF, they're all about refining the model's response to a given instruction.
Up until this point, yes. But the most cutting-edge research takes the next logical step. It uses reinforcement learning not to tune the output, but to improve the instruction itself.
So we're flipping it. We're not training the model to give better answers. We're training an AI to ask better questions in the first place, to create a higher quality data set.
That's exactly the idea behind systems like Teams-RL. Here, you use RL to train an instructor LLM. And this instructor's only job is to take simple instructions and make them more complex and diverse.
So it's an RL agent that's just a data curation specialist.
Precisely. Its actions are things like adding new constraints, like write this in iambic pentameter, or deepening the inquiry, or making the required format more complicated.
And what's the reward signal? How do you tell if an instruction is good?
The reward comes from another automated reviewer, LLM. It gets a high reward if the new manipulated instruction is semantically different from the original one, which forces the system to always seek novelty and complexity.
That sounds like a hyper-efficient way to generate the exact kind of diverse, difficult instruction data that was so expensive to get from humans in the beginning.
It's a massive win for efficiency. This RL policy learns the fastest way to create high-quality, complex data, and it dramatically reduces the number of queries you have to send to expensive proprietary expert models. One study showed it reduced those query counts by over 94%.
That kind of cost reduction makes state-of-the-art alignment accessible to way more people. But does this synthetic data actually produce smarter models?
The performance increase is significant, especially on tasks that need deep reasoning. For example, on mathematical problem solving, a model trained on this RL-generated data consistently beat larger models that were trained on just massive volumes of general data.
Can you give us an example of that?
There was a test with a complex polynomial for the function fx equal 5 pi s 2x plus 3. The model trained on this high-quality data got the right answer, 39. Several of the larger baseline models just failed, giving incorrect answers.
So it proves that a small, strategically difficult data set can teach reasoning skills better than a huge, generic one.
It can.
And you mentioned there's a privacy benefit here as well. How does this help with privacy?
Well, it inherently improves privacy because you're training the model on a small synthetic data set generated by an AI, not on vast amounts of potentially sensitive real-world user data. The risk of the model memorizing and leaking user information is just minimized.
And they were able to quantify that game.
They were. They ran membership inference attacks, which try to guess if a specific piece of data was in the training set. The models trained this way achieved an AUC score very close to 0.5.
Which, for our listeners, means the attacker is basically just guessing randomly.
Exactly. It shows the model has generalized the skill without memorizing the data. It's this amazing convergence of high performance, efficiency, and safety.
So to bring this all together, we started with this powerful but untamed statistical predictor. Then we gave it structure with supervised fine-tuning. The real breakthrough was RLHF, which used human preference to teach it taste, quality, and style.
And then the research moved into this era of automated alignment, using things like targeted human feedback to minimize labor, and now these advanced RL policies to generate superior instruction data synthetically. This whole journey is why you can interact with modern chat models as collaborative tools today.
The story really shows that the future of alignment is moving away from just throwing more data at the problem and toward optimizing the quality and efficiency of that feedback loop.
This focus on precision is what makes advanced AI controllable and sustainable. It shows we can get more reliable, more sophisticated models with fewer resources, as long as those resources are applied intelligently.
But I want to go back to that initial limitation we talked about with RLHF, the fact that it was so dependent on the subjective cultural preferences of that small group of labelers.
Right. That initial alignment was fundamentally constrained by the worldview of those few dozen contractors.
So if we're now automating this entire process, relying on models to generate and filter their own data, and relying on a reward model as the ultimate judge of quality, how do we make sure that we aren't just solidifying and amplifying those initial narrow perspectives across the entire globe? What happens when we try to align AI with truly diverse global human values as these techniques become more automated and less dependent on direct human oversight?
That is the central question now, isn't it? It creates a brand new challenge for the next generation of researchers, making sure that the preference signal we're automating isn't just efficient, but that it's fundamentally equitable and representative of the world the model actually serves.
That's certainly something to keep in mind as these systems become more integrated into our global lives.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.